Hey everyone, today we're going to talk about the question, how does a fall in temperature influence blood gas solubility and acid-base values? To answer this question, let's first answer the first part about temperature and blood gas solubility. Firstly, we need to understand Henry's law, which describes the amount of dissolved gas in solution is equal to the partial pressure at the air fluid surface interface times the solubility coefficient. So the solubility coefficient we know is inversely proportional to temperature, which means that for an increase in temperature, the solubility will decrease, so gas will come out of being dissolved. But if we decrease the temperature, more gas can be dissolved. So think of boiling water. As you increase the temperature of water, it will reach a boiling point where it will become gaseous and leave solution. Now, let's talk about CO2. So in blood, the total CO2 content needs to remain the same. So the amount dissolved is the same on this part of Henry's equation. But as temperature changes, the solubility coefficient of CO2 will change, which means that partial pressure has to change within that equation to keep the amount dissolved in blood the same. So we can see here that as solubility goes up with temperature that's decreased, the partial pressure needs to go down. Now, assuming everything else is normal, if I gave you a blood gas and the CO2, the partial pressure of CO2 was low, and I asked you what you think the pH would be, you would probably say the patient is going to be alkalotic, because if we think about the Henderson-Hasselbalch equation, if there's less CO2, the equation is going to be pushed more towards the left side of this equation. So you have less free hydrogen ions in the blood, so it's less acidotic. So you're going to have alkalemia. So that helps us answer that second part of the equation as well, but this is only one piece of the puzzle. As we decrease temperature as well, you have decreased metabolism and you get a lowering of the basal metabolic rate, usually around 7% per decrease of 1 degree below normal. This means that you get less cellular respiration, less CO2 produced as part of metabolism, which means that your partial pressure is going to be lower again. And then if we think about a solution, or we think about water, and it's H2O. So H2O, 2 hydrogen, 1 oxygen. And in solution, there's something called neutrality. And when you measure pH, the pH of neutrality is when there's equal hydrogen to hydroxide concentrations, or acid to its conjugate base. Now, through complex equations, we can actually then calculate that for every decreased drop by 1 degree in temperature, your pH will rise by about 0.015. Now, this is because as temperature drops, there's less kinetic energy within, for example, water molecules. So it'll stay more as a water molecule, H2O, rather than dissociation or dissociating and giving you hydrogen and its conjugate base, which will make the solution more acidic. So there's really 3 ways here that decreasing temperature has affected the acid base, and gas solubility is part of that. So why is this important to an anaesthetist and intensivist in clinical practice? And this is where the alpha stat hypothesis and the pH stat hypothesis comes into play. So in a normal thermic patient, when you take an ABG and you measure that blood gas, you're actually measuring extracellular fluid pH, and all the soluble gases and partial pressures are within that you're measuring. And at normothermia, this represents the intracellular environment. Not exactly, but if someone has acidosis and the normal temperature, it means that their cells are probably acidic as well, and that's why we try and correct it. Or if they're alkalotic, we try and correct it because we want intracellular pH to be normal, which is around 6.8, to allow normal enzyme functions, normal cellular respiration, metabolism, so that the body can function. But then in the scenario such as in cardiac surgery, where you're going to make someone intentionally hypothermic to try and reduce ischemia, lower that basal metabolic rate, and in some cases also stop the heart. You then need to ask yourself the question, what is the intracellular pH doing? So when scientists measured intracellular pH at different temperatures, they actually found that the pH remained constant at about 6.8. And what they found is that the imidazole groups on histidine, their pKa is about 6.8 at normal temperature, but as temperature decreases and increases, the pKa increases and decreases also, meaning that the ratio of unprotonated to protonated residues, which is 0.55 for these imidazole groups, remains the same throughout temperatures within reason. And this ratio is called the alpha. And this is where the alpha stat hypothesis comes into play. So the alpha stat hypothesis essentially is saying that as temperature changes, the intracellular pH remains constant despite the extracellular fluid pH changing with temperature. So we know that these proteins inside the cell function best optimally at the pH of 6.8. But then what about the proteins outside the cell? We know that the extracellular fluid environment becomes alkalotic with hypothermia. So should we be correcting this pH to maintain a normal cellular function or normal protein function outside the cell? This is where a different approach comes into play called the pH stat hypothesis, which hypothesizes that even though intracellular fluid pH remains stable, you should still correct extracellular fluid pH to maintain normal protein function outside the cell. But this inherently has its own risks, as you would essentially be needing to hypoventilate a patient to add CO2 to the system, which comes with its own disadvantages when compared to the alpha stat approach, where we don't correct the extracellular fluid environment unless there's derangement once the blood is rewarmed to body temperature, which I'll explain in more detail next. So if we compare and contrast our alpha stat approach and our pH stat approach, when we take blood from the patient, we take the blood from the patient while they're hypothermic in both cases, but it's the number that we put in the machine for temperature that changes. So in the alpha stat approach, what you will do is you'll put 37 degrees into the ABG machine, and the machine will rewarm the blood, measure the blood at 37 degrees, and base all the measurements on that 37 degree sample. With the pH stat approach, you put the patient's true temperature in, and the machine will then calculate what the partial pressures are based on that temperature. Now, all machines warm the blood up to 37 degrees, no matter what temperature you put in. But in the pH stat approach, the machine will then back calculate what the partial pressures are and what the measurements are, given the patient's temperature at the temperature you put in. So then, based on the sample taken from the alpha stat and what's measured once the blood's rewarmed, we would then correct whatever errors or whatever discrepancies there are based on the rewarmed blood. For example, we know that the blood coming from the patient will be alkalotic with a low partial pressure of CO2, but then once rewarmed, if the partial pressure of CO2 is normal and the pH is normal, you're not going to change anything that you do for the patient. But if it comes back acidotic or alkalotic, then you would manage the patient accordingly and then repeat the blood test to then see whether the changes you've made have resulted in correction. In the pH stat approach, you're going to put the blood test in at the temperature that the patient is, and you know no matter what, if the patient was normal before, there will be some derangement because of being hypothermic. So you'll get the blood, it will likely be alkalotic with a partial pressure of CO2 that is lower, and then you would then hyperventilate the patient to then increase the CO2 and decrease the pH to then correct for the temperature. You can see here that in the alpha stat approach, we're essentially ignoring what the temperature is doing to the patient while they're on the table. But in the pH stat approach, we're correcting what is happening to the patient on the table while they're hypothermic. The advantage of the alpha stat approach is that because these imidazole groups and the alpha is changing, you'll get metabolic intermediate trapping in the cytosol, and this is called the Davis hypothesis. you get preservation of these intracellular ions and enzymes and these ion channel function. It ensures optimal intracellular fluid buffering because these ematosol groups will be changing the alpha ratio with temperature. It preserves cerebral blood flow autoregulation and minimizes intracellular pressures or intracranial pressures. And this is because your CO2, you're not adding any CO2 to the system. It's remaining at the remaining at what it would be for the temperature. It also is said to minimize microembolization and strokes and prevent ischemic damage because you're cooling the patient and you're not adding CO2 to the system. The advantages of the pH stat approach is that you do get increased cerebral perfusion because CO2 is a vasodilator. So when you hyperventilate the patient and you increase the CO2 within the system, you're going to get vasodilation. And this isn't just isolated to cerebral perfusion, it's also to systemic vasodilation, which also helps with faster and homogeneous cooling as well. Now, there's also right shift of the oxygen hemoglobin dissociation curve with the increased PaCO2 that is put into the system. But this actually offsets the left shift that occurs due to decreased temperature and increased pH. So this initial left shift that occurs actually leads to more affinity for oxygen, which is a good thing in terms of it will allow more oxygen to cross from the lungs into the blood. But it's a bad thing in that it won't, or it's less likely to let go of that oxygen at the tissue level to oxygenate the tissues. So by adding PaCO2 to the system or increasing the PaCO2, you right shift the curve back to normal, which will help with offloading oxygen at the tissues. So as you can probably predict, an issue that you might run into towards the end of surgery is that if you were to adopt the pH stat approach and you're getting to the end of surgery and you need to start warming the patient up, all of a sudden the solubility of CO2 will decrease as the temperature goes up, meaning that your partial pressure of CO2 will also increase quite a lot, which will lead to a severe acidosis, which means that if you are to adopt the pH stat approach, you need to start hyperventilating the patient to bring off the CO2 or breathe it off to counteract this. While with the alpha stat approach, as long as the rewarmed blood has been in normal ranges, when the patient begins to rewarm, all of the pH and PaCO2 should settle back to normal ranges as expected. A disadvantage or a criticism of the alpha stat approach is that there's no established reference ranges for hypothermia. So although we rewarm the blood to normal temperature and assume that if it's in normal range, this is normal, we don't actually know what a normal expected range is within hypothermia for that hypothermic blood. So just to summarize, a decreasing temperature increases solubility, and as per Henry's law, the partial pressure will then decrease to maintain the same content. So for CO2, your partial pressure will go down. This means that you'll get the Henderson-Hasselbalch equation move towards the CO2 end as there's more buffering of hydrogen ions. So this will also increase your pH because there's less free hydrogen ions. You also get decreased cellular metabolism, so decreased CO2 being produced. And you also get decreased dissociation of H2O, so once again, less hydrogen ions that are available in the extracellular fluid, so pH will also go up. And it goes up by about 0.015 per 1 degree drop. And this is also known as Rosenthal's equation. We know that intracellular fluid pH remains stable despite temperature changes because of the ematosol groups and the alpha, which is the ratio of unprotonated to protonated residues, which normally is about 0.55 at a pH of 6.8, but changes with temperature so that your pH will remain the same within the cell. And then because intracellular pH remains the same, you're left with this problem where do I correct the extracellular pH or not? And this comes down to the alpha stat approach where you don't correct extracellular fluid pH unless there is a derangement once the blood is rewarmed, versus the pH stat approach where you will correct the extracellular fluid pH no matter the temperature